What if you're given a problem like this? Some circuit where you have two unknown voltages, V1 and V2. To solve that, we're going to use nodal analysis. This video is going to be a deep dive into how nodal analysis works and what you need to know to pass any test. If you want to just jump to solving this problem, feel free to do so, but let's talk about some background information first. So when doing nodal analysis, first thing you need to know is you're going to use KCL. If you're not sure what that is, click that link. And you're going to have variables that are the unknown node voltages. In one node of your circuit, so however many nodes there are, or n nodes, one of those nodes is going to be a reference. In other words, it's going to be ground. And ground is what every other node is going to be measured with respect to. So that symbol, and V will always equal 0 volts there. Now, n minus 1 linearly independent equations are needed to determine n minus 1 unknown node voltages. What does that mean? Let's say you have 3 nodes. How many independent equations do you need? 2 equations. Here's something that when I was taking my circuits classes completely threw me. So all this is given. Now V1 equals 4 volts, and here's ground. So V1 is 4 volts to here. So this potential is 4 volts. V2 is negative 2 volts. So that potential down to this node, this is all one node, it's negative 2 volts. So here's a question. What about V2 with respect to V1? Remember, V2 is negative 2 volts with respect to V3. But how do you find that? That would be V2 minus V3. So let's write that out. V2 minus V3. We know that V2 is negative 2 volts. We know V3 is 0 volts. It's negative 2 volts. So it seems obvious because we got that 0, but just remember, same principle. So now let's do V2 with respect to V1. Because we're going V2 to V1, V2 to V1. So that's negative 2 volts minus 4 volts. So we'll say V21 equals V2 minus V1, which equals negative 2 volts minus 4 volts, which equals negative 6 volts. What about V1 with respect to V2? So now we're going to go this way, V1 to V2. V12 is going to equal V1 minus V2, which of course is 4 volts minus negative 2, positive 6 volts. Seems like it'd be straightforward, but this is the concept that's going to throw a lot of people off when doing these larger problems. So truly understand this, and I think this is going to be the thing that will get you through. So use nodal analysis to find V1 and V2. We also have V3. Remember, this whole bottom node here is V3, but it's already solved for us because it's a reference. 0 volts. So V1, we don't know. V2, we don't know. V3, easy, 0 volts. So the first thing you need to do to make life easy, number one, look at what you got. You have 2 current sources right here. So you're going to use those to draw where you think your currents are going. And remember, these current lines that you draw, they can be wrong. You can get the direction wrong. It's just going to give you a negative when there should have been positive, positive when there should be negative. Because we need to set this up to use KCL. So 1 milliamp is coming in. So this is resistor 1, so let's call this, we're going to say I1 is coming down this way. Because 1 milliamp is coming in, we're going to say I2 is going this way. We have I2 going to V2, 4 milliamps coming down away from V2. We have resistor 3 over here, so we're going to say I3 is going this way. So there's I1, I2, I3. That's a 1 milliamp source, 4 milliamp source. Now let's do KCL for V1 and V2 because those are the unknowns. And as I work through this, I'm going to use all the units, I'm going to do all the steps. It might look tedious, but it's for demonstration purposes. So KCL, what goes in must come out, and it's all going to equal to 0. So 0 equals 1 milliamp going to V1. Now I1 is going out, so it's negative. I2 is going out, so it's negative. So minus I1 minus I2. Let's rearrange. So we get the 1 milliamp over there. That becomes negative 1 milliamp equals negative I1 minus I2. What can we do? Multiply by negative 1. And that's 1 milliamp equals I1 plus I2. Going to make life a little bit more straightforward. Now for KCL at V2. So 0 is going to equal, you have I2 going towards V2, so it'll be positive. Your 4 milliamp source going away from V2, negative, and I3 going away, so it's negative. So let's do I2 minus 4 milliamps, oh, sorry, getting a little close to my V3 there, minus I3. I2 minus 4 milliamps minus I3. Let's get the 4 milliamps over by itself. So we'll just add it over. Now we have 4 milliamps equals I2 minus I3. So now we just have to fill in what the i's equal. So let's go back to V1, and we're just going to work on this equation first. So we're going to have 1 milliamp is going to equal I1. Well, what's I1? This is where Ohm's law comes in. So we have V equals IR. Let's rearrange to get I by itself. I equals V over R. Super important. So I1 is going to equal V over R. Well, what's I1? I1 is going down, so it's going to be V1 with respect to V3. So V1 minus V3 over 12K ohm plus I2. I2 is V1 to V2, so it's going to be V1 with respect to V2, so it's V1 minus V2 over 6K ohm. And what does V3 equal? We know that's 0, so let's just show that it goes to 0, so we don't even have to worry about it. Now, we're going to split these fractions. Now we have 1 milliamp equals V1 over 12K ohm plus V1 over 6K ohm minus V2 over 6K ohm. Next, make your denominators equal. Forgive my little error there, that's a 12K ohm. So now that we have equal denominators, let's multiply everybody by 12K ohm. So now all the denominators are going to go away. And you have 12K ohm times 1 milliamp. And 12 kilo ohms times 1 milliamp is going to be 12 volts. Let me adjust one other thing. This is going to be a 1. So we have V1 plus 2V1 minus 2V2 equals 12 volts. So let's simplify. So that turns into 12 volts equals 3V1 minus 2V2. And that is equation 1. Now let's work on equation number 2. So we have I2 again, which from last time is V1 minus V2 over 6K ohm. But now we're going to be minus I3. I3 is over here. It's going from V2 down to the reference node. So V2 minus V3. And it's crossing over the 6K ohm resistor. But again, V3 is 0. So luckily, we don't have to worry about that. Let's split the fractions. V1 over 6K ohm minus V2 over 6K ohm minus V2 over 6K ohm. I say let's get rid of the 6K ohm first. So that goes away in the denominators, and it goes to the 4 milliamps. So 4 milliamps times 6 kilo ohms, it's going to be 24 volts. This turns into 24 volts equals V1 minus V2 minus V2. We'll simplify. And now that we see no real simplification is going to happen from here, what we can do, because we have V1 by itself, let's set the other parts of the equation equal to V1. So let's add 2V2 over the 24 volts. And that is going to be equation 2. Now we have a system of equations. Also, when you notice, we had 3 nodes, V1, V2, V3, and we have two equations to solve because they have two variables inside of them. V3 just disappears because it's equal to 0. So now we just need to solve this system of equations, and we'll have our answer. We already have V1, so let's plug equation 2, using what V1 equals, into equation 1. 12 volts equals 3 times what V1 equals from here, 24 volts plus 2V2 minus 2V2. Distribute 3 and simplify. We're going to subtract 72 over and get negative 60. And then we'll do 6V2 minus 2V2, which of course is 4V2. What's negative 60 divided by 4? Negative 15. Volts equals V2. So let's just plug that back in. And we'll solve for V1. That turns into V1 equals 24 volts plus 2 times negative 15 volts, which simplifies to V1 equals 24 volts minus 30 volts. So now what does V1 equal? 24 minus 30? Negative 6 volts. That's using nodal analysis to solve for unknown nodes. So now we have V1 and V2 figured out.